Okay, good morning. So we will start a new topic this Monday after we talked about surveys and experiments. Well, briefly talked about these two methods of data collection. So we said, whenever we start a um, where's my pen? Okay. So whenever we start a research project, right, we start with some kind of question, some kind of puzzle that we try to solve. Either, it's a sort of theoretical problem or academic question, right, that professors would like to solve, or some kind of business problem, right? So, for example, if your boss asks you, hey, Steven, or hey, Brittany, um, how come, the sales of our game this quarter is not as good as the sales of, in the previous quarter? So that's a question, right? And then what you need to do as a potential solver of this problem is to try to formulate this problem in a way that you can actually study, right? Instead of, keep this question in a very abstract level, you would like to make it more concrete. So what you will try to say is, well, let's try to, rephrase this question with some kind of concepts, right? So of course, the question that your boss just asked you is already a very, good question. The sales, right? Sales is a concept. It's also a variable, right? Because obviously the values of the sales of a game can change dramatically. So it's a variable. So your job here is to figure out, what causes the change of this variable, right? What causes, more precisely, the decrease in value of this variable that we call sales. But of course, what your boss asks you is an open-ended question, right? He asks, well, what causes the decrease in sales of the game? Um, so what you need to do is to, as we said, to make this question as concrete as possible. So you would then make some guesses, right? Which we call hypotheses or predictions, right? Hypothesis. So we'll say, the reason that, you know, um, the sales of our game has decreased this quarter is because the release of Pokemon Go. So there you go. You have a hypothesis. Pokemon Go causes or leads to the decrease of sales in your game, right? Decrease in, sales of game, right? Okay, so you know what it is. So this is a very good start of your attempt to solve this question, because now you have, two very well defined variables, right? The release of Pokemon Go and the sales of your game. And then, of course, you can start to collect data, right? Study design. So, given this question, you can start to design a survey to verify your hypothesis to see whether your hypothesis is correct or not, right? So you can say, well, let's ask people around to see if, whether or not people are indeed playing Pokemon Go. And whether, when people are playing Pokemon Go, they're playing other games or not, right? If, people are playing multiple games at the same time, then Pokemon Go cannot be the reason that causes the decrease in sales of your game. But if, Pokemon Go sort of occupies the majority of the time of game playing, then that could be a reason why you did not sell, your game as well as you did in the previous semester. Okay, so that could be your design, right? A simple questionnaire. Ask people, how much time you play Pokemon Go, how much time you spend, time playing other games, right, etc. All right, so multiple questions. All right, so this is where we, sort of stopped. Last week we talked about surveys, we talked about experiments, right? So those are different ways of collecting data. So people provide numbers when they answer these questions. Okay, so in other words, all these questionnaires generates numbers, right? Lots of numbers. Numbers. Okay. Numbers. Okay. So these questionnaires, for surveys, for experiments, generates many numbers. So, but then what do you do with these numbers, right? Um, what you need to do then is to analyze, of course, right? Analyses. So the next step after study design is data analysis. And, in other words, you're trying to make sense of the numbers that you gather. And it turns out that to analyze data, you need certain knowledge of statistics, right? So as you see, statistics is not just for scientists. It's for everybody. And later on, we'll talk about, now this is a perfect timing because this country is now undergoing general election. Well, soon. Well, the general election will soon to start, and in October, November, before the final results are released, you're going to hear lots of predictions, right? By a margin of, I don't know, 3 or 5. This candidate is leading that candidate, etc. So what do those numbers mean? What do you mean by a margin of something? When you say this candidate is leading that candidate by X%, does it mean this person is winning, or actually these two persons are still neck by neck in the race, right? So a basic knowledge of statistics, very important actually, is essential in daily life, in contemporary daily life, right? So a better way of seeing statistics is to see it as part of our literacy education, right? We should know something about all the classics, right, in literature, Shakespeare, Oscar Wilde. But on the other hand, we need some basic training in symbolic reasoning, and part of it is to understand how numbers work, understand how numbers can tell a story. Sometimes it tells a true story, sometimes it tells a false story. Then how do we know, whether or not the numbers are telling true stories or false stories? And how can we make use of the numbers for our purposes, right? To serve us better. Okay. Um, so that's why there's I designed this class to include a significant portion on statistics. So in the following few lectures, I don't know how many yet, perhaps 5 or so, or 4, depending on the progress. We're going to talk about what is known as descriptive statistics. So descriptive statistics are just for descriptive purposes. They're numbers or statistical techniques that are used to describe patterns, right? So survey studies can, describe patterns, but it can only describe patterns when we use certain statistical techniques. Okay, so this is our goal for those few classes, and after that, we're going to talk about what is known as inferential, right? Inferential statistics. Inferential statistics is not a more advanced statistics than descriptive statistics. It's just a different branch of statistics um, for a different purpose, right? Inferential or inferences, as you might guess. Well, it's, inferences about making guesses. You can sort of understand inferential statistics as how can we use numbers to make guesses, right? So descriptive statistics, how can we use numbers to describe patterns, right? So they're for different purposes, but very often these two types of statistical techniques are used jointly, right, to generate more useful information than when only one type of statistics is used. Okay, so all I'm asking here is, don't be scared about what you're going to learn in the next 3 weeks, maybe less than 3 weeks, because we have several days of examinations and Q&A sessions. Um, just be patient, right? Be patient. Be persistent. I will walk us through all the procedures, and in the end, you will see that statistics are actually not that scary, right? It can be fun sometimes, actually. Okay. Well, obviously, I would say that, but I'll leave you to make the judgment in the end. Okay. So descriptive statistics, as we just said, right? It is, it's a branch of statistical techniques that are used to describe patterns, describe features in more general terms of quantitative data, right? We said that surveys and experiments, they're quantitative methods, right? They gather numbers, they gather information that can be quantified in numbers. So, but when we gather a whole bunch of numbers, we try to see, first of all, whether there are certain features and patterns that we should pay attention to, and then we can go ahead to make guesses from those numbers about the things that we're interested in. Okay, so that's really, you know, descriptive statistics is generally the first step in running all kinds of analyses. So there are many types of descriptive statistics, but we're going to focus on two, the most important two types of descriptive statistics, or the two, most important features about any data that statistics will be used to describe. That is the central tendency of data and the dispersion of data. Well, more precisely, central tendency and dispersion are features of the distribution of values. The question, of course, is then, what is the distribution, right? What does it mean when we say values have distributions? Okay. So let's, make sense of this question, or understand this concept distribution by looking at two examples. So example one is a very simple one. So how much do you like iPhone in general, right? This is like a very standard survey question that you will come across in daily life, right? So I provide a scale for you, and it's not at all ranging. It ranges from not at all to very much, right? From 1 to 7. So all you need to do is to circle a number, right? Okay, so of course we cannot do this, face to face. I do not know what numbers you choose, but let's imagine, right? Let's imagine that we're doing this face to face, and then we have 5 people in this class, including me, 6. Okay, so this 6 are, we can imagine as 6 respondents, right? Me including me and the 5 of you guys. Okay, and then a surveyor or researcher will repeat this question for each one of us. Okay, so let's say the first person, I don't know who, so I'll just say the first person um, is going to give a number 1. Okay, um, okay, so let's do it this way. Scratch that. but we can leave these numbers on. So instead of using 1, 2, 3, 4, 5, and 6 to represent the 6 of us, we can add a number 7 here to represent the 7 values. How about that? Because we do have seven possible values, right? And this is me. Okay, this is Andrew Jiang. Okay. No, scratch that. I'm sorry. All right, so these, as I said, are 7 values, right? 1, 2, 3, 4, 5, 6, 7. Now, after you look at these questions, answer this question, I will ask you in turn, does anybody choose a 1? Okay, imagine there's one of you, right? One of you chose 1. So I would say, aha, there's one person that chose 1. Okay? Then I'll ask the rest of you, well, does anybody choose 2? All right, so let's imagine that nobody chose 2. And then I'll repeat the question, did anybody choose 3? Okay, turns out there are 2 of you choosing 3. Okay? And then I proceed, anyone chose 4, anyone chose 5. Turns out that there are 5 person, there are 2 people chose 5. And in the end, 1 person chose 6. Okay? And nobody chose 7. So you see, immediately we're seeing some patterns here, right? Seeing some kind of trend that is, at least among the 5, this is among the 6 of us, more people are holding some kind of a moderate attitude toward iPhone, right? Relatively fewer people are holding more extreme values, right? Extremely likely or not at all, right? So nobody are holding very few people, there's 1, but relatively fewer people were holding extreme values or extreme attitudes toward iPhone. Okay, so this is a distribution. Okay, how our numbers, how our these values are distributed across our sample, a sample of 6 people in this case. Okay, all right. We can look at another example. This time, we can look at murder rates, right? So FBI or some other branches of the government, or even among scientists, social scientists, they're very interested in the murder rates, or any kind of other rates, in this country. And they typically, one way to organize those numbers is by looking at murder rates by state, right? Which murder rates are number of murders, right, or cases of murders per 100,000 population. Okay. All right. So this is the table. Fantastic. We have all the states, right, from Alabama to Wyoming, right? All the states, including Alaska and Hawaii. Is there DC here? There's no DC. I don't see DC here. Okay, so it's just the states. Okay, so 48 contiguous states pluses the 2. Okay, Alaska and Hawaii. Okay, so here by the name of each state, there is a number representing, right, the number of the murder rates. Okay, so in Alabama, there's the rate is 11.6. That is, remember, right? So the actual rate is per 100,000 population, right? So obviously, higher numbers means higher murder rates. So which state do you see here has the highest murder rates? Louisiana, probably 20.3. It's not the most safe state in this country. Well, which state has the lowest murder rate? Is Hawaii, 3.8. It's pretty low. Montana is lower. New Hampshire is even lower. Oh, there we go. The champion is Maine. 1.6. Fantastic. Okay, anyway, right? So this table already is a kind of distribution, right? It sort of summarizes in a very crude way, right? And also very detailed way, right? How murder rates are distributed across all 50 states. Okay, but there's a problem. The problem, as we just saw, you know, going through, what is the state that has lowest murder rate, what is the state that has the highest murder rate. That these numbers, there are too many of them that our brain can hardly see any pattern from it. So if I ask you, how many states are there that has murder rates that's lower than 10, or how many states are there that have murder rates that are higher than 20 or higher than 15, right? Then each time you have to go through these numbers and make tallies. So that take time, right? So while this table is pretty informative, it is perhaps not the most informative way of presenting these numbers. So what scientists will do, of course, well, this is not to say that this table is not useful, right? It is useful when we try to pinpoint a specific state, but it is not very useful when we're trying to see the trend, okay? So what scientists typically do is they will come up with this kind of table, right? And they will first of all manually designate some kind of interval, right? So they break the murder rates. Instead of listing every possible single value here, they break the murder rates into several intervals, right? So from 0 to 2.9, from 3 to 5.9, etc. Okay? And then they will try to tally, okay, how many states will fall into each of these categories or intervals. So then we can see, what is the most, you know, what is the most common interval, so to speak, right? What is the most common interval of murder rates in America, and what are the relatively rare intervals for murder rates in America? Okay, so okay, I tallied all these numbers for you, because we obviously cannot do this, asking you to do this as we could in a face-to-face lecture. But okay, so anyway, tallying this is not very difficult. It just you need to be very careful. So here we see that there are 4 states that have murder rates that's between 0 and 2.9, and you have the rest. So if I ask you, okay, so I don't know, Crystal, what is the most common sort of murder rates in the United States among the 50 states? Then by looking at this table, you will have no problem, or everybody should have no problem in identifying the interval, right, of murder rates that's most common in this country, and that is 3.0 to 5.9, because there are 17 states. Okay, that's the largest number compared to all the rest numbers. And I verified that these numbers are correct by summing them up, and the sum is 50. Okay, so this is also a distribution, and this tallies, the distribution, how these intervals are distributed across the 50 states. Okay. All right, so now we can sort of have a more formal definition of what we call frequency distribution. So frequency distribution is essentially to list the number of occurrences, right, or the number of times that an outcome of a variable occurs. Okay, an outcome simply means a value that this variable can take, right? So in terms of our first question, the variable is the liking of iPhone. Okay, the liking of iPhone. So this variable, obviously, as we just saw, can take the value from 1 to 7. And we tally that, how many 1s, how many 2s, how many 3s, all the way to how many 7s, right? Other than we actually observed. The second variable we'll look at is murder rates, right? Murder rates. Obviously, this is also a variable because this rate varies across states. And what we did is we tally, the number of occurrences of each interval, right? From 0 to 2.9, I believe that's the first interval, right? So how many times these intervals occurs across 50 states? Okay, so that's what we mean by, a listing of the number of times that each possible outcome of a variable occurs. That is, each possible value of a variable occurs. So obviously, as you saw, the possible outcome can be concrete values or exact values, right? 1 or 2 or 7, right? Or it could be intervals of values, right? And this is most useful when the values don't repeat themselves. That is, as we saw in this case, right? Rarely, you have exactly identical numbers. That gives you too many numbers. In this case, 50. Well, if we're going to tally the murder rates across the world, when you have 200 plus countries and geographic, geopolitical regions, then you have 200 plus numbers. That simply is too many, right? In that case, using intervals will be very useful. Okay. So frequency is very useful and is commonly used in many contexts. And there are different types of frequencies. So what we just saw are frequency counts, right? We simply count how many times. 1 time, twice, 3 times, 4 times, etc., right? We also call those absolute frequency. But what absolute frequency mean can vary, right? Sometimes, the same frequency, the same absolute frequency can mean different things. And if we don't, specify the context of this, absolute frequency, we might have, the wrong conclusion. So, for example, we can say that there, a frequency. We can say that there's a frequency of 5, right? But this frequency of 5, has very different meaning when we say we count that this outcome occurs 5 times out of 10 occurrences, or we observe 5 times occurrences out of 100 trials, 100 attempts. So obviously then 5, this number here, has different meaning. 5 in this context means, actually it means half. Half of the time we'll observe a particular outcome. But 5 in this context simply means this outcome is very rare, because 5 out of 100, that is 1/20th. That is 0.05. Am I correct? God, my math's a little rusty. 5 out of 100. Yeah, exactly, 0.05. That means 5%. That means this event in this context is, after all, not that common. It's very rare, actually. Okay, so that's what we mean. Absolute frequency is useful, but it can be misleading depending on how many numbers, how many trials, or how many total occurrences that you have. Okay, so that's why we need a second type of frequency, and we call it relative frequency. And relative frequency is very close to will mean by probability, right? So the definition of relative frequency is this. It is the proportion. Now it's not the absolute number, right? It's a proportion. It's a ratio of the observations with which the value is associated, right? And it is calculated by, right? So you have the number of observations associated with the value. So let's say the value that you're interested in is your liking of iPhone, the liking of iPhone, right? Liking of iPhone on a 7-point scale. So you're interested in, how many people scored 7. So the value that you're interested in is 7. Okay? And how many people score 7? Well, in our example, 0. Okay? So there are 0 observations associated with the value. Well, let's 0 is not interesting at all. So let's imagine that actually there are one person, right, score 7. So the number of observations associated with the value 7 is 1. But then the next thing we need to figure out in order to calculate relative frequency is what is the total amount of observations? Okay, and we need to divide this 1, the number of observations associated with 7, by the total amount of observations. So total amount of observations simply is sample size. That is how many people we surveyed. Okay, because if the sample size, let's say the sample size is 5, that means we have 5 observations. That is, we have 5 numbers, providing that each person provides 1 number, right? So the total number of observations in most cases will be equal to sample size. Okay, so here will be, in our example, we say that there are 6 people because the number should include me, right? 5 of you plus 1, so 6. So number of observation is 5. Okay, so now we have the relative frequency. That's 1 over 5. That is 0.2. Okay, and sometimes this relative frequency is also expressed as percentages. Okay, and that's very easy to convert this fraction number to percentages. You just simply times 100, right? That gives you 20%. That means 20% of the people that we surveyed indicate extreme liking of iPhone. How about that? Okay? So now we can start to complete this table, right? So in the previous attempt, we only have the absolute frequency, or the frequency counts, right? There are 4 states, 15 states that have, a moderate score, falling in this interval. 12 states have moderates falling in this interval. And the total amount of observation is 50 because we have 50 states. Each state provides a number, so we have a total of 50 occurrences or 50 observations. So then it's a very easy matter to convert these absolute frequency to relative frequency and then to percentages. We simply divide 4 by 50. That gives you 0.08. And 0.08 is easily 8%, right? Then you can do the rest, right? So 17 divided by 50, what's that? 17 divided by 50. That's 0.34. 34%. Okay? 12 divided by 50. 4 divided by 50. 1 divided by 50. Okay, so that's very easy, right? But my question is, even without doing the calculation for all these different cells, my question is, if all these numbers, right, adds up to 50 because there are 50 states, what will be the number here? What will be the total relative frequency? And what will be the total percentage? Even without doing these calculations. Okay? You want to pause to think about it. But, if you already have the answer, um, I can tell you right now, right? Presume that you have thought about it. The answer here should be 1, and the answer here should be 100%. That is, all the relative frequency should add up to 1 for any particular sample, and the percentage should always sum up to 100% for a particular sample. Okay? Well, you may ask why. Why is that the case? Okay? So, okay, I'll give you a very simple proof, which should make sense. Okay? So let's just use this example. Because we know, right, relative frequency equals to the sum of proportions, right? So we know the common denominator here is 50, right? Because we always divide a absolute frequency by the total number of observations. That give us one relative frequency. Okay, so here's 4, but I want to generalize beyond this example. So we say this is x1, right? We don't have to know what this x1 is. It can be any number as long as it's between 0 and 50, right? It could be 50, it could be 0, but it can be larger than 50 because any single category, the frequency count for a single category cannot exceed the total number of observations. Okay? And then we have a second relative frequency, which is x2. It can be 17, it doesn't have to be. And then a third is x3, and all the way to, I don't know how many. I can say, they're at most 15 numbers. Okay? Now, because all these numbers, all these fractions have a common denominator, we can simply write or simplify the sum into one fraction with one common denominator, that's 50, but then we have the sum up here as x1 plus x2 plus all the way to x50. Now the question is of course, what should all these numbers add up to? Well, we actually saw just a minute ago, as at least illustrated in this example, all these individual absolute frequency counts should always add up to the total amount of observations. So that means regardless what each of these values are, it can be 3, 4, I don't know, I don't care, but all these values, as in this example, they should always add up to the total amount of observations. It's 1. And the percentage for 1 is 100%. Okay, that's why. So that gives you a way of verifying your answers in the future, right? So whenever you're calculating relative frequency for a sample in the future, a simple way to verify your answer is to see whether these numbers add up to 1. whether these numbers add up to the sample size. Here is 50 because we have 50 states, and whether percentages will add up to 100. Okay, that's sort of a mathematical necessity. Okay, so previously we talked about how to use tables, right, to summarize frequency distribution, or the distribution of relative frequencies or absolute frequencies. But sometimes and many times people prefer to use graphics to summarize frequency distributions. And a very common type of graphic representation of frequency distribution is what we call histogram. So histogram is typically placed at a coordinate like this. So the x-axis is the values of the variables, right? All the possible values that a particular variable can take, right? It can be, in this case, 0, 2, 4, 6. It can be 1, 2, 3, 4, 5. It doesn't matter as long as these are values that this variable can take, right? On the y-axis, we typically use the y-axis of this histogram typically plots frequencies. Well, here I use percentages, but you can use absolute frequency counts, or you can use relative frequencies. So if you use relative frequency here, it'll be 0.25, it'll be 0.20, you'll be 0.05, right? Doesn't matter, right? Percentages and relative frequency are the same thing. You can also plot absolute frequency count. So this is one occurrences. This is, I don't know, right? Depending on the total sample size. But all I'm saying is y-axis can represent all three types of frequencies: absolute count, relative frequency, and percentages. Okay, then we'll use a bin to represent the percentage of occurrences, in this case, of a particular value, right? So in this case, it indicates that the value of 0 occurs for about, I don't know, 12.5% by just eyeballing it. The value of 1 occurs for, I don't know, around, I would say 18% of the time, and we can go on. The value of 2 occurs for maybe 17% of the time, and we go on. Okay? So in other words, the height of the bin, right? This is a bin, right? This is a bin. The height of the bin represents its corresponding frequency. So the number of this 4, so this 5. The value of 5 of this variable occurs for about 20%, right, of the time. So bin height represents frequency. And of course, what's down here can be exact values, or it can be, interval values, right? It could be that, this bin represents from 0 to 2, this bin represents from 2 to 4, this bin represents from 5 to 8, right, etc. Right? It could be intervals, right? Doesn't matter. Depends on, of course, your purpose, right? So here are some rule of thumbs, which I think can be skipped because we're not doing the actual plot here. Okay, so there are second type of graphic representation of frequency distribution, and that we call bar charts. We just saw histograms. Well, histograms is for plotting continuous variables. So recall, we say that there are different types of variables, right? We have continuous variables where the values of the variable fall on a continuous continuum. Okay? So we also call those continuous data, or those data are, of interval and ratio types. But histogram is usually not used to plot nominal or ordinal data. and nominal data will be categorical variables. Ordinal variable is also categorical variables, but the category of ordinal data is ranked, right? So an example of nominal data will be male, female, right? Male, female. And ordinal data could be education level, right? So can you say, okay, so in our data, um, here's percentage, how many men and how many women were included? You can say, well, in our sample, there are maybe 45% of men, whereas there are 55% of women. So this will be a bar chart, right? The two bars. So in a histogram, right, these guys will be called bins. But in bar charts, obviously they're called bars. Well, they're just different names, right? But for the same purpose. It indicates the percentage of a particular value that a variable would take. So men, women, they're the values that the variable gender. Gender is the variable, and gender can take two values at least, right? Men, women. Okay, and here the y-axis represents the percentage or frequency of the occurrences of these two values. Okay, so this is nominal data, right? Nominal discrete data. But at the same time, we can also plot ordinal data. Ordinal data, we said that they're just, categorical variables, but ranked, right? Education is a very typical type of, ordinal data. So we can easily tally, right? For example, how many people in our sample has a bachelor degree, how many have a master's degree, and how many have a PhD degree. So here, my example is a categorical variable, right? Family type. So this bar represents married couple with some children. This bar means married couple without children. This single mother with children, single father with children, and the rest types of families. Okay? So a very notable difference between bar charts and histograms is that the bars in a bar chart representing all these different values variable, they have a distance or space between each of them, each pair of them. And this space indicates that these values, right, they are discrete. They don't overlap, right? They don't form a continuous continuum. But if you pay attention just now, in a histogram, the bins, right, they are very closely clustered. They touch each other, so to speak, right? And there's no space between each of the two bins. That means all these bins representing the values, right? Representing values that form a continuous continuum. They are not discrete, right? And that's why there's no space between the bins, whereas there is space between the bars. So that's how we distinguish, right, categorical variable or nominal ordinal data from continuous variable or interval ratio data. Okay, so histograms are for interval ratio data or continuous variables, whereas bar charts are for nominal ordinal data or categorical variables. Okay. So now we understand distribution, right? A description of the how values are distributed across a sample, or the listing of the number of occurrences of certain value in a sample. Out of the total amount of occurrences, we can talk about sample distributions. Of course, that will be the frequency distribution of observations of a sample, and then we can talk about population distribution. That is the frequency of distribution of observations of the target population. Actually, we have already seen these sample and population distributions. So if you recall in our first assignment, when I asked you to determine whether women or men in a sample is over or underrepresented, I actually give you the information I give you are the population and sample distributions. So for example, I said, in the population, for every the ratio between men and women is 2.3 over 1.7. So that's essentially a distribution, right? We can easily plot them, right? So here is men, here's women, and this is the ratio, and this is sort of the frequency, right? So man is 2.3, women is 1.7. The bar for women is lower, and it's a bar chart because gender is categorical, right? And then I then told you, in a sample, the distribution between men and women is about, I don't know, I'm making things up, 2.0 to 1. Okay. And then I ask you, in this sample, which gender is over represented? So, the question aside, essentially I'm telling you, here is the population distribution, here is the sample distribution. Is there a match between the sample distribution and the population distribution? Right. So easy enough. Okay. So now you see, these distributions are very useful. Okay. And of course, we said that, the sample distribution almost always will have some kind of discrepancy, will deviate, in other words, from the population distribution because you're only obtaining a subset of the people or individuals from the population. And because of this random process, there will always be some kind of differences between the sample distribution and population distribution, right? A very intuitive, property for sample distribution is that as the sample size increases, right, the sample distribution almost always will approach the population distribution. Okay, that is, will become more and more similar to the population distribution. That is, imagine, excuse me, imagine we have a population of 100,000 people here, right? And then we calculate that the gender ratio of the population distribution of gender is 2.3 over 1.7. And if we only sample, let's say, 5,000 individuals from this 100,000 individuals, then the sample ratio will be kind of similar, but will always deviate from the population distribution. But here we're saying that as we increase the sample size from 5,000 to 10,000 to 50,000, right? This ratio will become more and more similar to this ratio. Okay. And another property is the sample histogram, right? Representing the sample distribution or sample ratio will, becoming more and more like a smooth curve, right? We can easily imagine how this happens. For 100 people, imagine now we have 100 bins, right? In this histogram. So we can still see, the exact shape of these bins because there are only a limited amount of them. But as we increase the sample size to 500, from 100 to 500, you can imagine we need to split all these bins into narrower ones. Okay, And as we increase this, the number of sample sizes, we have narrower and narrower, thinner and thinner bins. And when, the sample size become very, very, very huge, essentially in the end, we can ignore the boundaries of all those bins and see the distribution as a smooth curve, like this one. And of course, the shape of the curve does not have to look like this. Well, we know this is normal distribution, but it doesn't have to look like this. It can be of any shape, right? It can be a shape of very weird form. Doesn't matter as long as it's smooth. It's sort of a curve, right? That's what it means. Now, once we have the distributions represented in curves, we can start to talk about the different types of um, histograms or distributions in terms of the shape, right? So imagine this is a very beautiful distribution. Well, it is very beautiful distribution. That simply means, right, most of the values, right, so these are extreme values. So this, this sort of distribution says, or histogram of distribution says, sure, there will be very extreme values, extremely large values, extremely small values, but these values will have very low frequencies. That is, they don't occur very often. They exist, but they don't occur very often. In contrast, the values that are moderate, right, not extreme, they will occur more frequently because, they are higher, right? Imagine we have some kind of bins under these curves, right? Under this curve, then we see, well, indeed, it has higher, larger amount of frequencies than these values, which will have lower bins. Okay, so this is what this normal distribution means. But we don't live. Okay, so now here are some nice properties about this normal distribution. It's bell shaped. It looks like a bell. Okay, let's clear all these now. It looks like a bell. It's symmetrical. That is, if I impose a line through the center, the two halves are exactly the same, right? We can sort of flip this half over, and these two halves should match, overlap perfectly. And most of the values, as we just saw, right, fall to the midpoint. Here's the midpoint, right? Very low, very high midpoint. So most of the values will be clustered around the midpoint, and extreme values are rare. Okay, so these are the properties of this bell-shaped curve. Oops. What's going on? And we call this part of the curve a tail. Okay, this is the center, this is a tail, and this is also a tail. Okay. Now, it is also very common actually, right? We saw this type of curve, and we call this type of curve a right skewed curve because we have a tail that's stretching to the right. Okay, so this is left, this is right. So we have a tail. Whenever we have a longer tail to the right, we say that this curve or this distribution is right skewed. That simply means, right, we have more extreme. You have, fewer extreme values toward this end. Actually, pretty, a larger amount of extreme values at this end. And of course, the values, right, is not at the center because this is the center, right? Most of the values will be clustered toward this end. And toward this end, there are fewer values, right? Because, obviously the area under the curve, this portion of the curve, is larger than, I'm sorry. Because obviously if this is the center, right? The area under this part is obviously larger than the area of this part. So that means there are more values clustered toward the left, to the left of the mid value, and there are fewer values clustered to the right. When do we see this distribution? We see this distribution when we have a very difficult examination. Imagine on the x-axis we have the exam scores from 0 to 100. Okay? If this examination is very difficult, that means more people will have low scores and only a few people will have the perfect score. Okay? Most of you here will be 50. Right? Fewer people will have 100. In contrast, we can have the left skewed distribution, right? That means in this case, right, most of, I'm sorry, eraser. It means that in this case, most values would occur to the right of the midpoint. So midpoint's here, right? So most of the values will occur to the right because the area under, in this part is obviously larger than the area under this part of the curve. Okay? So this will happen, as you can also imagine, when we have an easy examination. That is, lots of people will have, very high scores, but, very fewer people, right? Far fewer people will have very low scores. Okay? So there are common properties between these two skewed distributions. Of course, they're asymmetrical, right? That means if you impose a center line and you flip this portion of the distribution to this part, they will not overlap, obviously, right? So that's why they're asymmetrical. And as just said, most values will fall to one side. For the left skew distribution, most scores will fall to the right side because for left skew distribution, the tail is longer to the left side. That means more values to the right. In contrast, for the right skew distribution, the tail is longer to the right. That means there are fewer scores here, but more scores to the left of the midpoint. To the left side, in other words. Okay? Alright, so this is our first class on descriptive statistics. So we talk about the definition of descriptive statistics, and we then define what distributions are, right? Frequency, absolute account, relative frequency, percentages, and then we talk about the different plots, right? Graphic plots of the distributions. Okay, so we'll continue tomorrow to look at how can we use numbers, right? So far we use graphics to represent distributions. Tomorrow we'll be looking at how we use numbers to describe data. Okay, see you tomorrow.